created by MindSticks Foundation Trust.
Hello, students, and welcome to today's Explainer. Today, we're going to master quadratic equations, and we'll do it in 4 clear steps. First, roots to equations. Second, understanding the discriminant. Third, tackling real-world word problems. And finally, practice and applications. Let's dive right in.
Part 1, Roots to Quadratic Equations. We're building this from the ground up. Okay, so far, you've learned how to find the roots if you already have the equation. But what if we do the exact opposite? Let's say we already have our roots, those Greek letters alpha and beta. To build the equation, it's actually super simple. You take x squared, subtract the sum of the roots multiplied by x, and then add the product of the roots. Set the whole thing equal to 0. In math terms, that's x squared minus bracket alpha plus beta times x plus alpha into beta equals 0. It's a really elegant formula, isn't it? Let's quickly solidify this with an example straight from your textbook. Imagine the examiner says, find the quadratic equation if the roots are -3 and -7. We're going to follow our steps methodically. Step 1, find the sum. -3 plus -7 gives us, well, -10. Step 2, find the product. -3 times -7 is a positive 21. Finally, step 3, just substitute these values right back into our master formula. We get x squared minus -10x plus 21 equals 0. And, since a minus and a minus become a plus, our final beautiful equation is x squared plus 10x plus 21 equals 0. Boom, it's really that straightforward.
Moving on to part 2, understanding the discriminant and unlocking the hidden nature of roots.
Now, we're going to add a powerful new tool to our mathematical toolkit. See this little triangle? That's the Greek letter delta. And in quadratics, we call this the discriminant. The formula for the discriminant is simply b squared minus 4ac. Does that look familiar? You'll probably remember this exact piece from right inside the square root of your main quadratic formula. Because it sits right there inside that root, its value literally decides what kind of roots the entire equation is going to have. Now, memorizing these 3 conditions on this summary table is an absolute guaranteed way to secure marks in your exams. Listen closely. If you calculate delta and it equals exactly 0, your roots are real and equal. If delta is greater than 0, so a positive number, the roots are real and unequal. And finally, if delta is less than 0, meaning it's a negative number, the roots of the equation are not real numbers. Make sure you keep this table firmly in your mind, okay? All right, on to part 3, real-world word problems. This is where we apply algebra to daily life. Now, please don't be intimidated by these students. A lot of people find this part challenging, but honestly, it's just about translating long English sentences into simple math equations. Let's ground this abstract math in reality with Mr. Ratnakaro's rectangular onion storehouse. The problem tells us the length of the base is 7 meters more than its breadth. So if we just say the breadth is x meters, the length automatically becomes x plus 7 meters. By using the Pythagoras theorem with the diagonal they gave us, we can set up a perfect quadratic equation. So when we go ahead and solve that equation for the onion storehouse, we get 2 roots, x equals 5 and x equals -3. But wait, here is your golden pro tip for today. Length is never negative. We've absolutely got to apply real-world logic to our algebraic answers. A physical storehouse literally cannot have a negative length. Because of that, x cannot be -3. We just confidently discard it and accept x equals 5 as our true breadth. Makes sense? Let's look at another classic type of problem you're going to face all the time: speed and distance. Here, a train travels 360 kilometers at a uniform speed. It says that if the speed is increased by 5 kilometers per hour, it takes 48 minutes less to cover that exact same distance. By simply equating the time taken at the normal speed and the new speed, and, of course, remembering to convert those 48 minutes into hours, we can build a brand new quadratic equation to find that initial speed. And this brilliantly illustrates our real-world logic check once again. Solving the train's equation gives us x equals -50 or x equals 45. So what do? We ask ourselves, can a train travel at a negative speed? Obviously not, right? Speed is never negative, so we throw out the -50. Our logical final answer is that the initial speed is 45 kilometers per hour. Always do this logic check at the end of a word problem. Finally, part 4, practice and applications. Let's test your knowledge. You know what? You are now fully equipped to tackle your assignments. Just look at the wonderful variety and practice set 2.6. You can really see that quadratic equations aren't just numbers stuck on a page. We can use them to solve everything from predicting people's ages, to finding production costs for earthen pots, to figuring out the best way to plant trees in an orange garden. To make studying a bit easier, I highly recommend grouping these problems into common themes, just like we've done here. For instance, you've got age calculations, like the ones for Pragati and Vivek. You have speed and distance, featuring trains and riverboats. You've got geometry problems involving the areas of shapes. And work and time problems, too. When you start recognizing these patterns, you'll instinctively know exactly which mathematical approach to pull out during your exams. Let's just highlight one of those geometry problems really quickly. Look at trapezium ABCD. You're given the area as 33 square centimeters, and the lengths of the parallel sides are given as algebraic expressions, x and 2x plus 1. By just plugging these into the formula for the area of a trapezium, which is half into the sum of parallel sides into height, you create a quadratic equation. It perfectly blends your knowledge of geometry shapes with your brand new quadratic problem-solving skills. Okay, let's simulate a quick classroom test from problem set 2. Here's a multiple choice question for you. Which of the following quadratic equations has roots 3 and 5?
Okay, let's simulate a quick classroom test from problem set 2. Here's a multiple choice question for you. Which of the following quadratic equations has roots 3 and 5? I'm going to pause for just a second so you can calculate the sum and the product in your head.
All right, got it? The correct answer is option B, x squared minus 8x plus 15 equals 0. Did you get it right? The logic here is exactly what we learned at the very start of this explainer. The sum of 3 and 5 is 8. The product of 3 and 5 is 15. Substituting those into our formula, x squared minus the sum of roots times x plus the product, we land right on option B. Beautifully done. As we bring today's explainer to a close, I want to leave you with this really inspiring reminder straight from your textbook. Quadratic equations are useful in daily life for finding solutions of some practical problems. Remember, algebra isn't just a random collection of numbers and letters meant to confuse you. It's actually a super powerful tool designed specifically for decoding the real world around us. So my final question to you today is, what real-world problem are you going to solve next? I highly encourage you to go out and tackle the rest of problem set 2 with your newly found confidence and clarity. Apply the logic, double-check for those negative lengths or speeds, and trust your formulas. Thank you so much for learning with me today, students. Happy studying.